Thanks for that great introduction. Yeah, so funny story, I was here basically a year ago, and so a lot of what I'm going to be talking about today has to do with work that I started actually as a postdoc here in the Vision and Learning Lab. So to motivate my talk, I wanted to sort of transport you to what I hope is a familiar situation for you. Say that you're in a city, in this case, New York City, and you're going just from one place to another, okay? And as you're basically walking by, I want you to think about all the things that you're doing to actually get to that place. Isn't it amazing how we reason about space, how we figure out the general direction we want to go? We take advantage of our visual stimuli in particular to avoid obstacles, both dynamic and static. And even more, we reason about interactions that are happening nearby. And obviously, we're not just taking necessarily the shortest path unless we're really in a hurry, but we're actually becoming part of the social fabric of that particular environment. And so this sort of set of problems that I just described that we pretty much solve without thinking about it is something that has fascinated for a while the robotics and the human-robot interaction community. And the good news is that, well, we've come very, very far along in terms of creating systems that we can deploy in particular applications, maybe in the case of manufacturing or delivery, or even in the case of transportation. And so for many of you today, especially here in the Bay Area, it might seem like navigation may be a solved problem. But the reality is that if you keep reading the news, well, there's still very important challenges that remain. And I argue that a lot of these challenges come because of the complexity of unstructured environments. As soon as you put these machines somewhere where you haven't really done a lot of testing, where you don't know exactly how people will behave, then things start to break down. And so today what I'm going to do is I'm going to present to you a couple of different projects, all of them sort of surrounding the idea that structured approaches that sort of like in a classical systems engineering and even in a classical robotics way decompose a big challenge into smaller, simpler problems, they can help us reason about space. And in particular, the sort of commonality among these methods that I'm going to be describing is that they all use data-driven methods, in particular deep learning, in order to do complex function approximation. And what do I mean by this? What do I mean by complex function approximation? So in the world, there's lots of physical and social things that are happening around us. We can use deep learning as a mechanism to approximate these phenomena and then hopefully take advantage of that both for perception and decision-making in the case of human-robot interaction, and even more broadly in the case of HCI. And so what I'm going to be talking about exactly today, so those three projects on the left, I'm going to start with what I consider to be one of the simplest and more important challenges, which is traversability estimation, especially for avoiding getting your robot into troublesome situations. And then I'll start talking about problems that are, in a way, at higher level reasoning, more related to interaction, including navigation and reasoning about spatial behavior that might happen during social conversations. And then finally, I'll talk about some future directions, both things that I think are important that we need to solve, but also some exciting questions in relation to social influence. All right, so how many of you have heard about traversability estimation before? One, all right. So for those of you that have never heard about this, the question here is the space in front of the robot safe for it to traverse or not? Right, very simple binary question. And in a way, you can think about it as a software solution to an emergency stop, right? Whenever you might see, say, the Jackrabbit project that I was working on before here at Stanford, you might see someone behind the robot with ready to press a button, right? That looks like, oh, I'm going to stop the robot. This is basically an alternative or a complementary solution to do that through software. And so in this particular project, what we were trying to do was answer this question based on an image, in particular, an image capture from a camera with a fisheye lens that has a wide view of the environment. And based on that image, then we wanted to say, OK, what is the probability that the environment seen from that image is safe for the robot to traverse? And here the assumption is that that camera is on the robot, and that's basically what's going to come up in front of the robot the next time. Now, from this image, this might seem like a very simple problem, right? We just have to look for kind of empty hallways. But even if you go and collect data for this problem here at Stanford, then you soon realize there are lots of different scenarios that might come up that may pose challenges. And so what makes this even harder is that these challenging scenarios are the ones that you actually don't want to expose your robot to, because probably it's going to be in trouble very soon after it sees these images, right? And so because of that, what you end up having when you try to apply machine learning to this problem is an uneven distribution of lots of positive examples, things that are safe for the robot to see, which you can easily collect, and just a few negative examples of things that you were willing to expose your robot to get at least some negative data of what might be troubles or circumstances. And so this uneven distribution naturally is a problem for standard supervised learning methods. And what we do in this case is treat it as an anomaly detection problem. Our goal here for traversability estimation is detect these images whenever they come in the view of the robot so that it doesn't hopefully collide or fall down the stairs, whatever that is. Now, how do we implement this? So the method that we propose is called Gonet. It takes as input an image of the environment, as you saw before, and then internally is going to generate an image that looks like the input, but that also is constrained to look traversable. Okay? How do we do this? So have you ever heard about generative adversarial networks before? Raise your hand. Yeah, so I don't even have to explain this. So what's happening here is we have lots of positive examples, right? We can use a GAN to train a generator function that, given some noise input, will give us an image that looks like a positive example, right? But then in order to make this image that is being generated similar to the input, then we also train an inverse generator function once the generator is fixed in order to find what should be the noise that we pass to the generator so that we get something that looks similar to the input, okay? What does this mean in practice? Well, if your input is actually traversable, then the two images would look similar. But if your input is not, then the two images would look more different because the images are constrained to look as if they were traversable. And so based on that, we can use very simple features, even like the difference between the images pixel-wise, in order to finally classify whether the input image is traversable or not, here using a small set of positive and negative examples. And so why does this work? Well, this process, in a way, is sort of projecting the input space into a space that hopefully is easier to classify based on these features. Okay, you can think about it that way. Now, here's an example of how this looks in a video. So what you're going to see on the left is the input image captured from a robot. On the right, you have the predicted image. And then in the bottom, you have the probability that that space is traversable. As the robot starts, it's in front of an open hallway, so the two images look more similar. What's going to happen next is that the robot's going to turn towards the elevator. Pay attention there, because then the images will change a lot, okay? So now suddenly, boom, the elevator disappears. It looks like a hallway again. And even the person that you're going to see here also becomes sort of a static element. And it's not until the robot goes back into the hallway that images look more similar. That's what actually helps detect traversability, okay? You can see even the paintings in the walls disappear because they're not common across the data set, right? Paintings might be specific to specific places. Now, the original method that we designed here, it assumed that all the images are independent. You know, every time you get an image, you run your particular method and then you get a prediction. But this is, of course, not true for images captured by a robot because, well, the images are going to be correlated across time, right? You actually have video. And so in order to account for this, what we did was we added a recurrent neural network to the method in order to enforce temporal consistency of predictions. The other thing that we tried was actually adding 2 cameras to the robot. And here the hypothesis was, well, if we have 2 views, hopefully we can detect the differences between the views, and this will give us a hint as to whether things that perceptually look as if it was traversable but actually look different in the 2 cameras are at a given distance from the robot. So this is basically trying to use implicitly disparity among the images to try to predict traversability. And so here you have some quantitative results on a data set that was collected at Stanford. This data set is huge and it's actually available online. So if you Google Gonet, you'll get access to all of the data if you wanted to play with it. What we're comparing against here is having a Kinect on the robot, which is sort of the standard approach that you might use if you have the type of robot that we had before. The Kinect is nice because it has a depth image that already tells you information about how far things are. Then the second method here, the Siamese network, is basically state-of-the-art features for object detection and now assemble for the two images together in order to predict traversability. And then you have the basic version of Gonet, the one with temporal consistency, and then the one that uses the two views. And so in general, Gonet tended to perform really well. What was surprising to me, though, is that here the Kinect did not perform better. And I think this has a lot to do with the type of images that we were using, which have a very wide field of view, versus the Kinect, which has also a way narrow field of view. And as well, sometimes the noise in the depth of that sensor is pretty noisy. Yeah?
Do you have any intuition what would happen if you had both a Kinect and your method? Could you get better?
My bet is yes, they probably complement each other. So I would not say, you should remove all of your lidars and depth sensors from your robots and then put this on. I would not recommend that at all. I would say probably you want to have this as an additional source of information. Yeah. All right, so let me show you some examples here actually in this building. So this is the robot that, in this case, an operator is controlling. And what the operator is doing is basically sending velocity commands to the robot. And internally, we're using Gonet to stop linear velocity commands that will keep moving the robot forward whenever the probability of traversability goes down. And so in this particular case, the operator is kind of telling the robot to go against the glass wall. And if you see that red tape here, this is because we're using only one camera. Sometimes you'll see a video with the two cameras. And those are actually the fisheye views that you saw before. So that stop was actually Gonet. Now you might wonder, well, how can this do this if this is actually glass, right? Sometimes we even bump into glass. And so my hint here is that actually this line on the ground is very informative for what's happening. Here's another example. Now here we're using the two cameras. You can see the operator on the right. So we did a bunch of experiments where we just threw things in front of the robot trying to see if it would stop. Not everything is perfect, though. For instance, in this case, it stops, but there is that piece of cable under the robot which you could claim is a problem. So anything that is really small, anything that looks very similar to the ground, of course, because of visual features, can be an issue. So that's why I was saying probably it's good that you complement this with other approaches. Now, the fun experiment here is that all the data we used to train this method was collected indoors. And at some point, the first authors of this paper, they decided to try out, well, what happens if we actually run it outdoors? And so what happened here was we have a person. This is Noriaki, first author of the paper. He's holding now the fisheye camera as if he was a robot. He is also blindfolded and holding the laptop in a backpack. And then what we did was we connected the output of Gonet to a voice alert so that whenever the traversability estimation went down, the probability went down, then the system advised the user. So let me show you how this looked in this case.
Warning, danger. Warning, danger.
Now, this is surprising that it works at all if you've ever worked in deep learning, because there were no images outdoors in the data set that we were using. And so in a way, this was actually very, very telling for us that this method has potential to generalize to new situations than what it has seen before. All right, so that's my story about traversability estimation. I'm now going to switch gears to say, now that you can stop moving, let's start thinking about how to get to a place. This is what we normally called A/B navigation. And I'm saying here this is social because we not only care about getting to that destination, but we care about getting there in a way that hopefully feels appropriate for the people nearby, in a way that we consider to be socially acceptable. And so for this work, the main assumptions are that, one, we have a map of the environment, okay, so we don't have to solve mapping. We also can localize the robot so that we know, given that map, where it is at any given time. And we can also detect people and track them. And that tells us, relative to the robot, where are individuals that might matter for the navigation task. Now, if you were to implement this with sort of a regular system, this is what it might look like. This is a hierarchical controller, where you would have a global planner that takes that map, the goal where you want to go and your current location, and say, OK, this is general direction that you want to follow. And then you would have a reactive controller that would take sensor data and then predict velocities, both linear and angular velocity, to adapt to the things that were not in your map, to the things that are dynamic in the environment. And so In practice, this looks something like this. So say this is your robot. And then here, all the green lines are LiDAR returns. So you have a sensor that measures distance. And based on where the robot is and whatever the sensor says, then you can start computing costs for your environment that allows that reactive controller to basically figure out how you should move around the environment to not collide with all of these different elements. If you have something like a person, you might assign special costs to it to, for instance, model personal space, even model interactions if you know that people are coming together, and so on. Now, what is the challenge of these approaches? Well, it turns out that depending where you want to run your robot, depending on the type of social context, you might want to set different costs for the things in your environment. And there might be a lot of hyperparameter tuning that you have to do in order to find what is the right set of costs that will give you the behavior that you actually want at the end of the day. And so because of all that tuning that has to go on, recent methods have started to look at implementing that reactive controller now using machine learning, right? The hope is that, well, we can now optimize for what those parameters should be as a function of where the robot wants to go and sensor data. And in general, if you do this with, say, imitation learning, the other assumption is that the example data that you have, it encodes what it means for the robot to navigate appropriately. And that also saves us from actually having to explicitly write down what it means for the robot to navigate in a good way based on people's opinions. Now, remember, this is a big assumption. So ultimately, we always want to test after the fact with people to check if what is happening kind of makes sense. And so what we do in this work is take a similar approach to this, but we add a structure to this problem such that, one, we can have a little bit more interpretability as to what's happening under the hood. And second, hopefully, we get to a better behavior than you would get with just a black box. And so in this case, what we have is a local planner that will predict a modification to the global plan. This is what we call the local plan. And that's going to adapt, again, to the dynamics of the environment. And then we're going to have a velocity controller that takes that local plan, information FG here is features from the global plan, and information from the sensors here, this is LiDAR information, to then output velocity commands for the robot. And so how does that look in practice? Here's a video of a simulation. We have pedestrians, simulated pedestrians moving around. We have static obstacles. We have a goal that we want the robot to reach, and a global plan that was computed based on the map of the environment. Note that this global plan is not ideal because it's actually coming very close to a person in that point, but that person is not in the map. So there's no way that the high-level planner knows that. And then what the robot has to do is predict based on all that information what velocities it should actually execute in order to get to the destination. Now, our approach also outputs this predicted local plan, which is a visualization in a way of how the robot is going to be moving in the environment. It doesn't have to follow it perfectly, but it kind of hints to you how the robot is going to go about what's seeing at that point. And so if things are going well, you should see that local plan sort of adapting to the dynamic elements. And eventually, when the robot reaches the goal, hopefully it stops, and it reached the destination. Now, one of the challenges when we were working on this problem that came about, and I think this is a common challenge in general in HCI, as soon as you start working with many different types of sensor data, is how should we combine all the information that is coming into our modules here, both the local planner and the velocity controller. And sort of the standard thing that you might do is just concatenate all the features together into a bigger feature vector and then process that along. Now, what happened in our case is that if we just did this, the robot would pay attention to one thing more than the other. And so we said, let's be smart. Let's add more features for the things that it's not paying attention to. And they would actually pay a lot of attention to those things and not the other things that it was paying attention to originally. And so because of that, we decided to go with sort of a dynamic set of combination for these features. What we're doing is computing attention coefficients for each of them as a function of what their values are. And in this way, based on whatever the context is where the robot is navigating, it would basically scale some features more than the others to pay more attention to that particular source of information. So let me show you here how this looks. So this is a plot for the inputs to the velocity controller. And then on the y-axis, you have that attention coefficient for each of them. When the robot starts moving, when it's close to a dynamic element, the LiDAR becomes more important. As the robot starts basically moving around free space, then the local plan, what it has to follow, becomes more relevant. And then at the end, when it starts approaching the global plan, then the global plan, the end destination, then the global plan becomes more relevant. And so it was nice to see, right, even though we were not supervising these attention coefficients, this is something that could be learned from data based on how the example trajectories that we had to train this model looked like. Now, we compared this method against other approaches, in particular, sort of a classical approach like the one that I described before, where you hand-tune the costs for things in your environment, and also two deep learning methods that kind of work as a black box. The first one here just takes 1 point along the high-level plan that the robot has, and this point is at a fixed trajectory, at a fixed distance from the robot. And then the one over here actually takes a sequence of points from where the robot is up to a given distance. And then we compare that with our proposed approach. Here's an example video of all of these methods running in practice. What you'll see is that in general, our approach is not necessarily the most efficient, but it definitely can handle sort of variations in the locality of the robot. And it can adjust to things that are happening by that were not necessarily part of the plan. In this particular case, these two other deep learning methods kind of got stuck. This doesn't happen all the time. This is just one example. But what you can see is, for instance, here, even this was troublesome because the robot came very close to a person there. What you can see is that in general, this is a very complex problem. And part of what makes it successful for a robot to do a good job here has to do with that spatial reasoning that we normally do without even thinking about it. So quantitatively, how did this method do? So what we have here are 4 different environments where we tested how it was doing. This is an environment that was very similar to the training data. And so we would expect, if we're doing things right, that these numbers will all be high. Even the parameters that we set for the navigation stack were chosen based on this particular environment. Now, if you go to a simpler environment where you have fewer obstacles, fewer people, same layout, then most methods perform better. Ours is a little bit down. But when you keep increasing the complexity of the environments, you either add more people or you move to a new layout. That's where actually the benefits, I think, of machine learning start showing up, and the particular structure that we gave to this problem. This, I must say, this is in terms of how often the robot reached the goal on a number of trials. That's what this plot is showing. Now, in this case, we were looking at how often did the robot come close to almost or nearby a collision, including collisions. Here, the threshold for considering a near collision was 0.3 meters. And what you can see is that in general, the navigation stack is sort of the most conservative of all, with our method being the most conservative out of the ones that are using deep learning in this case. Now, as I said before, it's important that we understand if the end result, right, if the behaviors that we're rendering kind of make sense to people. And so the first step that we did here was actually evaluate this perception using mechanical trick. And for that, we showed 12 different scenarios with these 4 methods to people. In particular, we had 35 people evaluate all of these methods. What we found in this case was that, in general, the approaches were considered to be natural, with the one of the black box deep learning methods being the most unnatural. This is the one that actually had a trajectory as input. We also found that methods tended to not be considered as aggressive. Note that this is evaluating videos, right? So it's not 100% telling you the full story. But at least it was good to see that these numbers were low. And also we found that our particular approach was considered to be more efficient in comparison to other methods. These 2 differences were marginally significant. And this to me actually was surprising, because when you look at the methods, it's really not rendering sort of the minimum path. But it seems like the way that it's adapting to the environment, people consider it to be more efficient than the other approaches. Now, how well does this transfer to the real world? Well, we don't know yet. We're trying to answer that question. This is a very, very early video of the robot executing the policy that we train in simulation. It's not perfect, but at least we're starting to see cases where hopefully we can run this on the real robot, which is in general a hard thing to do in robotics, because transferring from simulation to real world is difficult because of the differences in the input distributions. One of the biggest challenges here, I must say, is actually people tracking, which is not as consistent as is obviously happened in simulation. And so now if you see this robot around, be careful, because we might be testing the new approaches that we're implementing on it. Don't assume that the robot works perfectly, which many people sort of do. All right, now moving on, I want to talk about an even higher level set of reasoning problems which have to do with understanding human spatial behavior for the purposes of interacting. And this problem, this is something that I started working on while I was a PhD student. I was working here with Disney. And we had made this furniture robot that we wanted to show to groups of kids that came to the laboratory. And so the whole setup was as follows. So people came to the laboratory. They started interacting with the robot. They didn't know it was going to be there. And sort of the storyline of the interaction built up to a point where the robot gave them a set of souvenirs for having come to the lab. And then soon after they got this piece of paper that you see here, crazy things happened. People did not pay attention to the robot anymore. The members of the conversations changed even more. New conversations started right in front of the robot, even though it was still speaking and trying to engage the children in that environment. And so when this happened, we kept wondering, right? What can we do in order to enable robots to understand that these interacting groups are actually changing right in front of it? And it might be that the environment is noisy, but it's very clear for us, even from these pictures, that these groups are changing, right? And so now the interesting bit here is that as we were watching videos, spatial arrangements kept emerging, like very regular spatial arrangements, like side to side or face to face or circular arrangements, whenever these conversations were happening. And turns out this should not be a surprise. There's lots of work in social psychology that describe the way that we position ourselves relative to one another during these social interactions. What we try to do in general is maximize our opportunities to monitor one another's mutual perceptions. And this naturally results in these types of formations. Now, how does this work in practice? So we all have what is known as a transactional segment. That is just this space that extends forward from our body that includes whatever we're engaged with. And whenever we hold conversations, we naturally position and orient ourselves so that we intersect our transactional segments with one another. And that way we have equal, direct, and exclusive access to the space between us. And that's what leads to all these different kinds of formations that I assume you're very familiar with. Now, a lot of my work in my PhD focused on verifying the hypothesis that this also happens in human-robot interaction. And in fact, we tried this basically in the experiment that I showed you originally, also in a case where the robot was playing Mafia with groups of people, and also in another experiment where people were brainstorming ideas with the robot. In all these cases, these types of formations tended to emerge. And so then the question became, how can we recognize these formations automatically using computational methods? And at the time, the way that we proposed to do that is as follows. We had information about the position of people in the scene, information about their lower body orientation, which is sort of the main feature that matters for transactional segment. And then we modeled O spaces. We tried to find whatever the transactional segments of people intersected. And then we say, aha, if there's an O space, there's probably a group going on. Now, the twist here is that you can also use information about the groups that are happening at any point in time in order to better estimate people's orientation. And the reason why this happens is because interactions are naturally a force that biases the way that people stand in human environments, right? If I were standing here all the time giving my back to you, probably you wouldn't feel so comfortable with all the information that I'm saying because it would not be clear if I'm actually talking to you at this time, right? And so we use this particular method in order to study body orientation and gaze. Here in this particular case, we had the robot basically orienting two different ways. This is a between subject experiment. In one case, the robot oriented towards the middle of its conversational group, as computed automatically by the method. And in another case, it turned towards the person who was the speaker or the addressee at that given time. And then we also had the robot change its gaze during the interaction. And basically, we have here 4 conditions combining each of these variables. What we found in this case is that in general, when things went wrong, this completely disrupted the interaction, right? People wouldn't know what is going on. And so it's actually very important for robots to conform to the way that people expect them to be positioning themselves in these environments. The other thing that was interesting was that the particular gaze behavior that we tried influenced the perception of the robot's motion. And vice versa, the motion that the robot was executing, whether it was oriented towards the middle or it was the attentive orientation behavior, it influenced the perception that people had of the gaze of the robot. And because of this, even though often we design these behaviors independently of each other, I think that we should rather try to do it jointly in order to account for these potential effects of one into the other. Now, at the time, a lot of the experiments that I did were simple open spaces. And if you look around, right, there's many environments where the type of formations that you see, they're actually malleable to that context, right? If you enter, for instance, an elevator, people might be okay kind of coming closer to one another because, well, obviously the space is more constrained. Similarly, if you're in a party where there's lots of people around, you might actually change the distances in your proxemics behavior based on what's going on. And so because of that, then we decided to try, in this case, again, data-driven methods, and now reframe the problem as a clustering problem from a sort of more classical perspective. So here, say that you have a scene, right, of people interacting. Then you can build a graph where every node corresponds to a person. And then the edges, if they have a weight, that weight corresponds to how likely it is that people are actually part of the same conversation. And so provided you have some algorithm to do graph clustering, which exists for the case of conversational groups, then the question that remains is what should be the weights, the affinities that you assign to those edges in the graph so that you end up having a good result when you try to cluster people out, right? And so for that, what we did was we proposed to use a neural network, again, because it has great approximation capabilities in this case for this type of social phenomena. And so the way the system works is we have as input a social scene for which we have position and orientation for everybody in that scene. Then we build a graph that I mentioned before. And then for every edge, we're going to compute an affinity value that depends on features of the dyad that we care about, which are just the nodes related to that edge, but also on features of all the other people in this scene. If this scene was very big, then you would just pick the people nearby the edge that you care about. And so how does these two transforms look like? They actually look very similar. What we have as input is information about the position and the orientation of people. Here, this is 4 numbers just because we're encoding the orientation with cosine and sine. And then the other 2 numbers are just x and y. And then we pass this through a transformation that gives us features in a higher dimensional space. And then we use a symmetric function here in the same spirit of PointNet, which was used to reason about point clouds, in order to get one feature that is irrelevant of the order of the inputs. So in this particular case, this is a max pool operation. You could use another symmetric operation potentially. Okay. Any questions about this now? All right. Now, once we have all those affinities, what we can do is we run our clustering algorithm. Here in particular, we use an algorithm called dominant sets, which is actually a generalization of maximal clicks for weighted graphs. Now, what kind of results do we get in this case? So these are 2 data sets for group detection within the computer vision community. The first graph here, the first blue bar, corresponds to a deep learning method that was proposed very recently. This green bar actually corresponds to another algorithm that is similarly reasoning about graph clustering. And then the yellow one is actually state of the art in this particular 2 data sets now for 2 years or so. And so for the coffee break data set, we do as well as state of the art. The challenge here is that this data set has orientations for people that are binned into 4 possible numbers. And that makes it actually really hard to notice small variations in people orientation. Now, in the cocktail party data set, where the orientation is actually way more fine-grained, then in this case, we actually outperform the state of the art. And the nice thing, I think, of this approach, which makes it very straightforward to implement, is that, again, we're not finding all the parameters of what exactly should be the transactional segment for every people in the scene, which is some of the things that you have to care about for GraphCut's approach. All right, so for the remaining time that I have, 10 minutes or so, I want to talk about some future research directions, which I think we're not going to be able to avoid, and others that I just think are interesting and fun to think about. So one question that often people ask, especially within human-robot interaction, and I think HCI as well, is why are we using neural networks? And my answer to this is that, well, if you look at how well they perform against other learning algorithms, there has been a clear advantage, and we want to take advantage of that sort of powerful capabilities of these methods. The challenge here, though, is that for most problems that have to do with interaction, you're actually in this space where you don't have that much data. And so a natural question arises of how do we get more data, right? So that we can actually take advantage of these methods for what we want to do. For the case of navigation, and in particular for the case of robotics, I'm a big advocate for just getting data from the real world. I know this is very expensive, but I think it's going to be very fruitful in the long term. And so that's one of the things that we're exploring in particular in the Jackrabbit project here at Stanford. Another thing that you might want to do is actually take advantage of simulations. Simulations, of course, are not going to be perfect, even when you think about simulating a person. That's very challenging on itself. But it might actually allow you to make progress faster and prototype algorithms in a way that hopefully doesn't take forever for you to get an answer of how well things are working. This particular type of simulation environments here, we're using Unity. I think there's lots of potential for using all of the different game engines that are coming along, that are becoming available now for this kind of work. One of the also interesting positive things of these environments is that you can very easily export your games into online form, which means that you can potentially engage a bigger amount of people than if you had to bring everybody to your lab to try out your environment and then basically use it in person. Now, in terms of sample-efficient methods, I think there's also very interesting potential for revisiting ideas from topological navigation for the case of enabling robots to move around human environments. And so when I'm saying here topological navigation, this is what I mean. So say the robot wants to go from one place to another, sort of as we wanted before. But now instead of modeling the environment precisely with a metric map, as kind of what we were assuming we had in the prior example, we're going to have a graph. And this graph is going to now be a more compact representation of that space. Here, the nodes corresponds to places where it's sort of a critical situation where you want to make potentially a change in decision in terms of where you're going. So think about it like entryways or exit ways from other places, even points along a corridor whenever you can change direction one way or another. And then the edges in this particular case encode connectivity. That's sort of the classical view of topological navigation. Now, in this particular case, the twist of how we're thinking about this, taking advantage of data-driven methods, is that each of these edges can also correspond to a particular behavior that the robot can execute to go from the source node to the target node. And if you think about indoor environments, there's often lots of things that you do that look very, very similar to each other, right? And so you can potentially have just a small set of behaviors, like the ones that you see here, that you can then compose with one another in order to get basically a complex navigation route. And so here, for instance, we're considering turning left behaviors, turning right, following a corridor, finding a door, and moving straight. Now, with these five behaviors that you see here, we can now enable a robot to go from that upper room over there all the way to this room simply by localizing relative to the graph, in this particular case using graph neural networks, and then executing, depending on the edge that you're in the graph, that particular visual motor behavior that is a deep learning policy for the robot. Now, note here that the robot is not using this map. It's just taking as input this depth image from the environment and the particular behavior that it has to execute. And that allows the robot to navigate all the way around to the destination. Now, this work yet does not consider dynamic elements. This is all in a static environment. But I think if we start thinking about how are we going to make robots really operate in human environments where everybody's going around. Every time I go to New York City, I go to the subway and I see how crazy it is, how people are moving. I think this type of approaches have slightly better chance than if we assume we're going to have a perfect map, metric map of the environment where we're always going to know precisely where we are. Because often, right, all the people around you will occlude you. Now, another sort of positive aspect of this type of work is that the semantics of these behaviors can make an easy connection to natural language directions. And so we've also explored taking natural language directions and then translating them to a sequence of behaviors using, in this case, the topological graph basically as a database or a knowledge base for this translation task. All right. Now, in terms of thinking more about kind of classical human-robot interaction problems, one issue that arises very often when you put a robot in a public space is the following. So this is a robot in Japan. This is Robovi. And the robot is in a mall. And when kids find it, they start doing all sorts of crazy things to the robot. And so one of the strategies in this work to help the robot was to actually have it move whenever it could move towards the parents of the kids. Because then, you know, the kids will behave a little bit better. And so this line of work is actually very interesting, right? Because it poses the question of how can robots take advantage of their social context in order to help themselves in these kinds of settings. And so to explore this question, we decided to run a lab experiment where we had a confederate, here the person on the left, interact with a participant, which you see on the right. And these two people, they were set to complete a distraction task, mainly a memorization task here on the tablet. And while they were doing that, there was a robot nearby that happened to be there because they were using it before for something else. And the confederate would fail at the task and then basically release its anger with the robot. And then the question was, how should the robot behave in order to motivate this person to help it out even a little bit? Okay? So let me show you an example of what this abuse looked like. This was both verbal and physical abuse, starting with verbal abuse and then combining verbal and physical. This is sort of like the worst case scenario at the end of this session. So this is the robot that you see there. And so a lot of people were in shock, no surprise. In terms of what the robot tried to do, so in one case, this is one of the variables we manipulated, which was the response from the robot. In one case, the robot did absolutely nothing, right? It was abused, and it just kept doing whatever it was supposed to do. In another case, in the shutdown response condition, it kind of showed a sad face for a little bit, and then it shut down for 10 seconds, and then it went back up, and then kept doing whatever it was doing. And then in the emotional response condition, the robot first became sad and then angry at the confederate. Now, the other thing that we manipulated was empathy, whether the robot was empathetic to the task that people were doing, how well they were doing in it, and whether it was just indifferent, right? It didn't care what was happening. What we found in this case was that even though we expected the empathetic robot to, in general, induce more helping behavior, there was no difference across conditions, and the majority of the people ended up helping the robot. And so this is actually good news for humanity, I think. Not for our experiment necessarily, because the results were not as significant, but I think it's good that people were actually, at the end, at least flipping up the robot, or even sometimes moving it away from the confederate so that hopefully it would not abuse it again. Now, in terms of the responses that the robot had, in general, the shutdown response was the one that led to higher ratings of the perception of the verbal abuse, and also higher distress from the participants. And so in a way, it seemed like this shutdown response ended up being sort of the more effective out of the ones that we tried. Now, this is just a very small baby step. I think it's important for us to think about this question, right? How can robots motivate pro-social human behavior? And potentially, right, if they could do this, then you could imagine that robots could leverage their social context for practical problems like the one that I showed before. But maybe they could also potentially just positively impact interactions more than we could ever imagine from the beginning. And so with that, I'm going to end thanking everybody that has helped on the many projects that I showed before, especially the Stanford Vision and Learning Lab. There was a lot of effort in the projects that I showed from the lab. And also our funding sources, Toyota, NSF, and Disney. And I'll open up for questions. Thank you.